In this video, we're going to prove that a function has an inverse if and only if it is bijective. So first, some definitions. If a and b are sets, a function from a to b is a triple f(a)(b), where f is a relation between a and b, so a subset of the Cartesian product of a and b, with two properties. First, in our formal definition of a function, we require that the domain of the function be all of a. So if a is an element of a, there exists a b in b, so that the pair a comma b is in f, or in other words, f of a is equal to b. And secondly, it passes the vertical line test if there are potentially two outputs, so a b1 is in f and a b2 is in f, so potentially two outputs for a, then actually they're identical outputs. b1 is equal to b2. So this is our formal definition of a function. We'll typically write, instead of writing the function as a triple f(a)(b), we'll use normal function notation and write it as f colon a arrow b, and read it as f from a to b. And instead of writing that the pair a comma b is an element of the relation f, we'll write f of a is equal to b. So the domain of a function is all elements a and a, so that for some b and b, a comma b is in f, or in normal function notation, the set of all a and a such that for some b and b, f of a is equal to b. Okay, it's the collection of all elements of a on which the function is defined. The range is the set of all elements of b, so that for some a and a, the pair a b is in f. Okay, so it's set of all b and b such that for some a and a, f of a is equal to b. Okay, so the range of f is the subset of b that consists of elements which the function actually hits with elements from a. Alright, so again, the range is a subset of b. We have a name for b though. B is called the codomain of the function. Alright, it's sort of the potential range. If a function satisfies this property, if whenever f of a1 is equal to f of a2, then a1 is equal to a2, we call the function F injective, or one-to-one. We say a function is surjective, or onto, if whenever b is an element in b, then for some a and a, f of a is equal to b. Okay, so everything in b is hit by the function from an element of a. Another way of stating this is that the range of the function is equal to the codomain. And we say a function is bijective if three things hold. The domain of the function is a, the function f is injective, and the function is surjective. Okay, if we have two functions, f from a to b and g from b to c, then the composite of these two functions, written g circle f, is a function from a to c, defined by g circle f, or g composed with f of x, is g of f of x. So it's g evaluated at the value f of x. If a is a set, the identity function on a is denoted I sub a. It's a function from a to a, given by I sub a of x is equal to x for all x in a. And finally, we define inverse functions as follows. So if f is a function from a to b, and g is a function from b to a, we say g is an inverse of the function f when g composed with f of x is the identity on a of x, and f composed with g of x is the identity on b of x. Okay, so g circle f is the identity on a, and f circle g is the identity on b. So the theorem we're going to prove in this video is that if f is a function from a to b, then f has an inverse if and only if f is bijective. So let's assume that f is a function from a to b. In part 1, we claim that if f has an inverse function, then it is bijective. Let's assume f has an inverse function, and let's call it f inverse of x. Okay, so we have two properties. We know that F inverse of f of x, F inverse composed with f of x is the identity on A of x, and F composed with F inverse is the identity on B. We need to prove that F is injective, surjective, and that the domain of F has to be all of A. So let's prove that F is injective. Let's suppose we have two elements of A, A1 and A2. And let's suppose that f of A1 is equal to f of A2. Okay, so we know that A1 can be seen as the value of the identity on A evaluated at A1. We know that the identity on A is equal to the inverse of f composed with f. We know we can evaluate the inverse of f composed with f as f inverse of f of A1. Now f of A1 is equal to f of A2 by hypothesis, so this is equal to f inverse of f of A2. And again, that's the definition of the value of f inverse composed with f at A2. But f inverse composed with f, of course, is the identity on A, so this is equal to the value of the identity on A at A2. And that value, of course, is A2. So we've shown that if f of A1 is equal to f of A2, then A1 has to equal A2. And that, of course, means that f is an injective function. Now let's prove that f is surjective. So let's let B be an element of the set B. We know again that B is equal to the value of the identity on B at B. And we know the identity on B is equal to f composed with f inverse. We can evaluate f composed with f inverse as the value of f at f inverse of B. Now f inverse of B, notice, is an element of A. So f goes from A to B, f inverse goes from B to A, so f inverse of B is an element of A. Okay, so the fact that f inverse of B is an element of A shows that there is some element of A, let's call it, so that f of A is equal to B. And that's what we needed to show that f was surjective. Okay, we needed to find some value in A so that f of A is equal to B, right? And of course that value is exactly f inverse of B. Okay, so let's show that the domain of f has to be all of A. If A is an element of A, then A is equal to the identity on A at A, which of course is identity on A is f inverse composed with f, and that's f inverse evaluated at f of A. Okay, so that means that f of A has to be the type of thing you can validly put into f inverse. In other words, f of A is an element of B, and so it follows that A is in the domain of f. So that proves that the domain of f equals A, and so we know that it's a bijective function. So in part 2 we'll prove that if f is bijective, then it must have an inverse function. Let's assume that f from A to B is a function, and let's assume that the domain of f is equal to A. Okay, so that means that we have a triple, so let's go back to the formal definition here. It's a triple FAB where the relation f is a relation between A and B. And we know that we have, for all A and A, there exists a B and B, such that f of A is equal to B, because the domain of f is equal to A. So that's exactly what that line says. It's the domain of f is equal to A. Writing this in the ordered pair definition, we can rewrite it as, for all A and A, there is some B and B, so that A comma B is an element of f. We also have the vertical line test requirement for a function, so if A B1 is an f and A B2 is an f, then B1 is equal to B2. In other words, if f of A is equal to B1 and f of A is equal to B2, then B1 is equal to B2. Every input has exactly one output. Okay, let's assume f is injective. We can write that as ordered pairs as follows. So if A1b is an F and A2b is an F, then A1 is equal to A2. Okay, that'd be the same as writing if F of A1 is equal to F of A2, then A1 is equal to A2. And finally, assume that F is surjective. So we can write this as a statement about ordered pairs, and we'd get that for all B and B, there is some A in A, so that AB is in F. Okay. So we've written all these properties of F as their ordered pair definitions so that we can easily use them when we define G. So now we'll define G. So we'll define a triple GBA, where G is the collection of all ordered pairs B comma A in B cross A, such that A comma B is in F. All right? So you can see we're sort of switching inputs and outputs here. And what we have to prove is we have to prove that this G is actually a function and that it's actually the inverse of F. Okay. Now, first of all, we know that G is a subset of the Cartesian product B cross A. Recall that we know F is a surjective function. So for all B and B, there's some A in A such that A comma B is in F. Now if we rewrite that property in terms of G, we get for all B and B, there is some A in A so that BA is in G. Okay, and that exactly says that the potential domain of G, which is B, is actually the domain. In other words, what it means is that the domain of G is equal to B. All right. Now let's prove that G passes the vertical line test. So we'll do that by first recalling that F is an injective function. So if A1b is an F and A2b is an F, then A1 is equal to A2. Let's let BA1 be in G and BA2 be in G. Okay. Then that means that A1b is an F and A2b is an F, right? And by injectivity, A1 is equal to A2. So that means that G passes the vertical line test. We gave it an input B with two potential outputs, A1 and A2, and by injectivity of F, it follows that G passes the vertical line test. Okay, so indeed we have a function then G from B to A. Its domain is B and it passes the vertical line test. That makes it a function. Okay, so now we claim that the inverse relations hold. So G composed with F is the identity on A, and F composed with G is the identity on B. So first we'll prove that G composed with F is the identity on A. So to do that, let's suppose that A is an element of A. Now we know that for all A in A, there is some B in B, such that AB is in F. Okay, so let's pick one. Let's pick B in B, so that AB is in F. So in other words, F of A is equal to B. Now AB in F means that BA is in G. So G of B is equal to A. All right. So we know that F of A is equal to B. We picked an A. We found a B in B so that F of A is equal to B. We know since AB is in F, BA is in G, so that means G of B is equal to A. And then of course that means that G composed with F of A is G of F of A. F of A is B, so that's G of B, and G of B is A. So G composed with F of A is equal to A for every A in A. And that of course means that G composed with F is the identity on A. Okay. So for all A in A, G composed with F of A is equal to A. So G composed with F is the identity on A. So now we'll prove that F composed with G is the identity on B. Let's pick some B in B. We have to prove that F composed with G of B is equal to B. So recall that for all B in B, there's an A in A so that AB is in F. So let's pick an A such that AB is in F. That is, F of A is equal to B. Since AB is in F, it follows that BA is in G. That is, G of B is equal to A. And so we get that f composed with g of b is equal to f evaluated at g of b. G of b is a, so that's f of a, which is b. So that proves that for all b and b, f composed with g of b is equal to b. And that proves that f composed with g is the identity on b. All right. So we have the two relations, the two statements we needed to prove to show that g is in fact the inverse of f. So that completes the proof, and that completes this video. Thanks for watching.